Welcome to The Explainer. I am just absolutely thrilled to take you on today's journey. We are going to dive into a topic that honestly completely rewrites how a lot of us think about the history of mathematics and computer science. We're looking at how ancient Indian mathematics laid the absolute bedrock for modern computational logic. If you've ever wondered where the underlying logic of the algorithms that run our digital world actually comes from, well, you are going to find this fascinating. Okay, let's jump right in. We're anchoring this explainer with an incredible observation from the 7th century CE by the Syriac bishop Severus Sabuct. He said, and I quote, "Indians possess a method of calculation that no word can praise enough, using 9 symbols." What he was marveling at here was the decimal place value system. Way before it was adopted globally, the sheer elegance of using just 9 symbols, and eventually a 0, to represent literally any imaginable quantity, well, it was recognized as completely revolutionary. This wasn't just some new way to write down numbers, it was a massively upgraded operating system for human calculation. In our modern education system, we tend to put things into very rigid boxes. We segregate the left brain stuff, like mathematics and logic, away from the right brain stuff, like poetry and literature. But if you look back at the ancient Indian tradition, you see a completely seamless blend. Mathematical formulas weren't locked away in dry, terrifying textbooks. They were beautifully woven right into poetry, literature, and everyday philosophical discussions. And this blend of art and math, it wasn't just to make things sound pretty, it was highly functional. Enter the concept of sutras. A sutra is essentially a pithy, poetic verse designed to compress and retain massive amounts of complex information. Think of it like a highly efficient data compression algorithm, but built specifically for the human brain. By turning a complex mathematical procedure into a rhythmic poem, they made it memorable, accessible, and completely eliminated the stress that so many people associate with learning math today. Let's ground this in reality for a second. Consider the Siana city. It's this magnificent falcon-shaped sacrificial altar dating all the way back to the Vedic age. This wasn't just folks throwing some stones together in a pile. The construction required exactly 200 precisely placed bricks. And not just any bricks. They had to be 5 differently shaped bricks, including squares, right-angled triangles, and even complex compound shapes like trapeziums. Building these altars was essentially the equivalent of solving a massive multivariable equation. The architects had to use a fixed total number of bricks, build in exact layers, and ensure the specific area of this falcon perfectly matched the area of completely differently shaped altars used in other rituals. Solving strict architectural constraints like this wasn't just basic masonry. It required an incredibly high level of geometric and algebraic mastery, which really acted as a catalyst for mathematical innovation. Section: the binary system and the number 0. So, when we think of binary code, we naturally think of the 20th century, right? We picture early mainframes and silicon chips. But we actually need to rewind the clock to approximately 300 BCE. This is where we meet the mathematician Pingala and his text, the Chanda Sastra. Pingala was analyzing poetic meters, specifically the combinations of short and long syllables in Sanskrit poetry. And to systematically classify all the possible combinations of these syllables, he inadvertently established the world's earliest known binary sequences. Absolutely wild to think about. And Pingala didn't just stop at basic sequences. He formulated rules to convert his binary syllable combinations into decimal numbers, and vice versa. He developed a concept called Muru Prastara, which is essentially Pascal's triangle, but centuries before Pascal was even born. He created optimal algorithms to calculate powers, and most importantly, his work shows an early conceptual use of 0 as a symbol to represent the absence of a value in his sequences. Which brings us to 0. It seems so simple to us now, doesn't it? Just an empty circle. But conceptually, it is arguably the greatest mathematical invention in human history. For a very long time, European mathematicians actually resisted the concept of 0 and negative numbers. They viewed them as absurd or meaningless, which kind of held European mathematics back for a while. But in India, the concept of nothingness, or shunya, had deep philosophical roots, so it was entirely natural for them to embrace it as a concrete mathematical reality. It was in the 7th century CE that a mathematician named Brahmagupta took 0 from being a mere placeholder and officially established it as a fully functioning, independent number. He didn't just use it. He wrote down the concrete algebraic rules for how 0 interacts with other numbers. He laid out exactly what happens when you multiply, divide, add, and subtract with 0, and even how it interacts with negative numbers. This was a monumental leap forward for computational logic. When you look at the timeline here, what you see is the sheer density and continuity of algorithmic theory building by ancient Indian mathematicians. You have Pingalat laying down the binary and combinatoric groundwork in 300 BCE, then Aryabhata in the 5th century CE, standardizing the decimal place value system and creating brilliant algorithms for square and cube roots. And that's followed by Brahmagupta in the 7th century, finalizing the rules for zero and tackling complex quadratic equations. Is a continuous, unbroken stream of high-level mathematical theory building passed down through the centuries.
Section: the algorithmic mathematical mindset.
The core characteristic of Indian mathematics is what we'd call today the constructive approach. In some mathematical traditions, the ultimate goal is just to logically prove that a solution to a problem exists. But the ancient Indian mathematicians, they were intensely practical. They wanted approximate, usable solutions for real-life situations. Think astronomy or architecture. So their emphasis was always on finding a constructive, step-by-step procedure to actually solve the problem. Put simply, they were writing algorithms. And the undisputed master of this algorithmic thinking was Aryabhata. He had this incredible ability to take highly complex, multi-step mathematical operations, like finding the square of a massive number, and encode the entire procedure into a concise, memorable, poetic verse. He was essentially writing source code, but in Sanskrit. Let's actually walk through one of these ancient algorithms. Take Aryabhata's recursive method for squaring a number. First, you square the most significant digit. Then, you multiply that digit by 2 and by each of the remaining digits to the right. Next, you remove that first digit from your workspace. After that, you shift over, the next digit becomes your new focus, and you just repeat the entire cycle. Finally, you add up the staggered results. Now, if you know anything about modern computer science, you'll immediately recognize this. It is a perfect, iterative loop function. He applied that exact same algorithmic logic to square roots, which, as you know, is notoriously difficult to calculate by hand. Aryabhata's methodology involves splitting a large number's digits into pairs, designating them into varga, meaning odd places, and avarga, meaning even places. By categorically sorting the data first, he created a framework where a systematic, repeating mathematical operation could be applied. Aryabhata's procedures operated recursively. He built a system that introduced and processed just one digit at a time, cycling through a specific set of rules over and over until the entire number was exhausted and the final result was achieved. He was executing a fully realized recursive algorithm, in his head and on parchment, literally more than 1,000 years before the invention of the first mechanical calculator. No way around it. That is just brilliant. Which brings us to a final thought I want to leave you with today. We've seen how binary sequences were born from the study of poetic meter. We've seen how complex recursive algorithms were memorized as beautiful verses. These ancient minds saw absolutely no boundary between the analytical and the artistic. So if poetry and algorithmic logic were seamlessly blended 2,000 years ago to produce some of the most profound mathematical breakthroughs in human history, what exactly are we losing by separating them in our education systems today? It's definitely something to chew on. Thank you so much for joining me on this explainer. Keep questioning, keep learning, and I'll catch you next time.